Okay, so let's just get started. Okay. So the topic I'm going to cover is mainly about the Druid anatomy, a brief introduction about Druid and use cases, um, various industry use cases. Okay. So welcome all once again. This is the 9th meetup in Bangalore. And this time we have gone virtual. Okay. So let's give maybe another couple of minutes for others to join. I'm expecting more people than this. So let's get, meanwhile, I have something for you to think about. So basically, when we talk about big data, sometimes back, even the big data was small data when we compare it now. Just want to think about what is the scale at which you have come across the data in your workplace. If you are relatively new, I will give you some idea about what a big data means, just for a better understanding that this is what the scale we are going to talk about in the next 30 minutes. Yeah, so just pick this figure from internet, given from where I picked this one. So basically, if you talk about the New York stock trading data, so this is about 4 billion transactions per day. So yes, this is a big data. But when compared to the other scenario of ad tech, where in an ad exchange, approximately 400 billion records or 400 billion transactions happens programmatically in a day. So when we talk about 4 billion and 400 billion, there are huge difference. So just wanted to make you aware that we'll be talking about the latency, everything in terms of this figure. And in a New York trade transaction, most probably approximately around 10 columns or 10 fields will be there. Whereas in an ad tech transaction, approximately 100 fields will be available. So it's wide and lengthy, big. Okay, so that's what I want to bring your attention to. Now, before we start, so this is something which I thought about how this is my personal feel when I was working with previously with multiple technologies. I have come across this kind of situation where I required sub-second response time, especially when I was working with the Hortonworks and Cloudera. I come across customers and I all wish for a sub-second latency query response over petabytes of data. Again, the next point which I was talking about is about scalability. This is another wish is the scalable database engine, which can execute the same set of code or same SQL in real-time data as well as in historical data. So the reason I tell you this is I've implemented a Lambda architecture. So while implementing, what I have done is I fired one set of queries to historical data, I fire another set of queries to real-time data, and I need to write code to merge this one together and bring the result to the program. Okay, so this is another wish. What if there is a generic implementation where I can fire a single query and the system, the database itself will capable of doing the rest of the things. Okay, so the next point is, I just want to, I always think about, okay, to take a step back. Previous to this, I was running a small startup. In the startup, the first page was a landing page where it shows some charts. So especially when you show the charts, what happens is that it's an aggregated query. This aggregated query hits the Druid or sorry, the aggregate query hits the database, and that is a really expensive operation. So aggregation, I just want to avoid. So how do? I aggregate the results and keep it in a pre-aggregated store, like something like a HBase or something like even a DB itself. And when the data is loaded, I mean, when the user logs into the application, the landing page, the data will be loaded from this aggregated table. Uh, of course, this is not real time, and it's not accurate to the point as of now. It might be accurate to the point as of yesterday, or maybe when the last aggregation happened. So this is one wish I had, to get in a real time, if I can get the result, that really it will be really good. And next wish I had was the cost of efficiency. I used Elasticsearch for some time to analyze the thread in my previous application, thread from the internet. I just constantly, basically, to monitor where the data, who is accessing accessing my application. It was working fine for some point of time. After that, it started giving me a bigger check for me to pay to AWS. So effectively, I have to shut it down and think about a different option for doing that. So again, this is my another wish. It should be cost efficient, and it should linearly scalable. Okay, for example, some point of time, when what happens is the Elasticsearch cluster started consuming a lot of money, and it's exponentially, the cost was increasing. So that's the reason I had to take a hard decision to shut it down. Okay. Yep. So this is the most boring slide. My name is Tijo. I haven't introduced myself. I'm senior solution architect at Imply, dealing with build data challenges since 2014. Yeah, that's it. So, I just wanted to give some more some more details of how you can ask questions. So I will post a link here, so that at the end of the session we can discuss about all this Q&A. So I will copy this here in the chat. Okay, so you can post your question there. We will discuss your questions at the end of the session. Okay. Yeah, so you are now aware about what I'm looking for, and really I got excited when I came to know about Druid. It satisfies most of my wishes. Okay, so in this session, what I'm planning to cover. There are a lot to talk about Druid, but a key takeaway from the today's session is about fast analytics, how Druid is capable of doing fast analytics, and cost efficiency, basically in terms of computational cost and storage cost towards the performance. And we will discuss about variety of use cases, how industry leverage Apache Druid to address different use cases. Also, I will give an introduction. Elena already told about the Powered by Druid page. I will introduce that page as well. You will get to know more about how Druid being used in production in multiple customer side. Okay. Now about Druid, a brief about it. Druid's open sourced in late 2012. It's basically from MetaMarket. MetaMarket is a AdTech analytics company. So the initial use case is AdTech analytics. And the scalability challenges were, the major challenges was that scalability, as you've seen earlier, there's a huge data which need to be crunched for analyzing the ad. And most often the ad relevance really increase, or the priority of the sorry for the distraction. Sorry, some mobile was doing. So relevance is more on the freshness of the data. Okay, so the highly relevant data is the newly added data. And data type is mostly streaming and in batch in nature. And it requires very low latency interactive queries because the ads are showed on a real-time basis. Okay. So this is the major challenge which Druid started to address. Now we'll see, this is for those who are not familiar with the Druid architecture. We will see how Druid, various components in the Druid interact with each other. So if you think about this, so you can think of a broker as a endpoint which accepts the query from the client. And we will discuss about this in detail in further slides as well. So broker accepts the request or basically SQL queries or even native queries and split it up into multiple small queries to historical and indexer. We'll talk about indexer in a while. And so the Druid hit the historical, different historical, and the historical returns the result back to broker, and all the data back is merged together or reduced together in broker and send it back to the client. So what I mean is basically here a map reduce operation is happening in that way. If you think about historical is a mapper where the data is stored in the historical and it fire the query, it will fetch the data and return the data to the broker, and broker merges that result back and provide the end result to the client. Yeah, so what is indexer then? So the data is ingested, as I this is a real-time data database engine. We'll call it that. This is something which supports a real-time data analysis. So what it means is that the real-time data can be streamed into the indexer. So indexer will read this data from Kafka or any other data source. And after that, it keeps that data into memory for some period of time. At the same time, indexer is capable of responding to the queries which brokers send it to indexer. So the indexer has some data which helps in its memory that will be processed and send it to the broker whenever a query is requested. Now, so this is at the high level. So basically, if you look at this, the mapping happens at historical and indexer, and the reduction operation happens at the broker side. Yeah. Now, once the data is ingested, as I mentioned earlier, it's in a raw format. So after a while, this data will be converted into a columnar format, and that end of that conversion, it will push it into a storage called deep storage. So it can be any distributed storage mechanism like S3, Azure, or Azure Blob Storage or GCS. So it will be pushed into the deep storage, and historical will pick those segments from the historical, from the deep storage. So that the flow goes, the data is streamed inside, it goes to deep storage, and it goes from deep storage to historical. And we have two other nodes called master nodes. What the main purpose of the master node is to coordinate various activities in the Druid cluster. Okay, hope it's clear for the time being, right? Yeah, so how we can load the data? So currently we support real-time ingestion from Kafka Kinesis and even Azure Event Hub based on the Kafka compatibility mode. So you can run Azure Event Hub in Kafka compatibility mode, and using that you can ingest the data from Kafka Kinesis or Azure. From the batch side, the data can be ingested from S3. Assume you have a file in S3, you can read the data from S3 and ingest into Druid. Okay, so we will have a small demo how we can load the data. So I will take the case of a HTTP. So assume that you have a data in a remote HTTP site. So we can use that to ingest the data here into Druid. Okay, so I'll share my screen. I hope you can see this, my entire browser, not just the slide. Can somebody type here in the chat? Yeah, okay. Yeah, so I have a Druid cluster which is running locally in my machine. So you click on load data and start a new spec, and I can click HTTP here, and it's asking for a remote URL for ingesting the data. So here I say that, okay, I provide this remote URL where Wikipedia data is available, and click on apply. So it reads the data and samples some of the rows and show you some of the rows here. Okay. So you can click on next. Basically, this is a wizard helping out to create a ingestion spec for you. So click on next. As you know that this is a time series database, so you need to identify which column is the time. So by default, I have one time column here. It automatically picked up that column here. And if not, you need to select the column and click on next. So during ingestion, you can specify any of the simple transformation. For example, some cleanup or something need to be done for your rows. And those can be done in the transformations page section. You can click what transformation you need to do it. You can apply here. I'm not going in detail how to do that. And you click on filter. So filter is assume if you want to ingest some specific data or eliminate some specific data. So those filters you can apply here, and after that you can click on configure schema. This is the place where you specify what all columns you need. You can assume if you want to remove some data from here, you can click on delete. Then the data will not get ingested. You can also specify whether you need rollup or not. We will discuss about rollup in the coming slide. So for the time being, let it be. Yeah. So the data, basically the segments are, since it is a time series database, its segments are stored based on the time. So you need to define a time interval at which the segments need to be created. If it is hour or day or anything, you need to specify that. This is for the organizing of the data inside the Druid nodes. In the segment granularity, for the time being, I'm selecting day. And I click on publish. Okay. So the data is getting ingested. So for time being, I'm just going here and I'm doing a select star here. Select star from Wikipedia. Okay, so this is Wikipedia is my table. So you can see the data is available here. Now, at the same time, this is SQL based. Assume if you want to convert this into a NoSQL. This is Druid supports two formats of querying the data. One is a SQL based querying language, or there is a native query language which is in the form of a JSON. So some use cases prefer doing native queries because it's in a JSON format. So ultimately, you can do a sorry, just skip here. So this is my SQL query. You can click on the explain SQL query, and you can select the native query. So Druid console itself convert the SQL queries and give you a native query. You can execute that here. Okay, so it's 100%. I'm missing a bracket. Yeah. Okay. So you have the result here. Okay. So let's go back. So this is about loading the data, and it's about executing a SQL or native query and getting the result. Druid also support connecting to JDBC, so you can use JDBC also to connect to Druid. Yeah. So we have seen the SQL and native way. Now, other topic which I want to cover is about how fast you can query this data. So basically, Druid solves the problem of low latency queries. So you can expect a result of sub-second level of latency over a huge amount of data, and it's support a very highly concurrent queries. Multiple queries can be executed at the same time. So that is one of the key advantage of using Druid. As I mentioned earlier, Druid is a implementation of Lambda architecture. So that means if you want to merge your result with your historical data, merge in the sense you have to query the real time as well as the historical, Druid supports that. So that is one advantage. And this can be done in sub-second level of latency. Yeah. So we covered what. Now we need to cover why. Why Druid is fast? Why not other system? So it's mainly because the way in which the data is organized in Druid. So, well, I just want to explain why. Just taking one set of example, one set of data. So here I've seen that this is a time series database. Timestamp is there. There are some dimensions. The dimension is page, username, general city, and we have some metrics. So metrics is nothing but the values maybe we want to do the aggregation on. For example, sum, min, max, and stuff like that. We'll be working and we'll be running on the metrics. Okay, so this is how assume the data is organized. Now look at this. So I just taken the first 3 rows and I'm trying to explain here. So why it is fast? There are 4 reasons. One is it's compressed. The data is compressed in multiple ways. One is it's zipped and kept it in the form of a segment. And second reason is the data is encoded in the sense like, so if you see this SF, so SF is replaced with 0, or sorry, 2. LA is replaced with 1, and we have one more record with the DC. Yeah, so the DC is encoded as 0. So it's instead of storing it as string, it's encoded as an integer. So which will take less number of bytes to store the data. So this is compressed. This is a kind of compression. It's called a dictionary encoding, and it's stored into the memory, right? So the dictionary is in memory. Now another reason is the Justin Bieber here in this case. Justin Bieber is happened to appear in the first 3 rows, right? So if you look at it, so the first 3 bits are enabled, okay? So which means that it's a kind of inverted index. We call it as a secondary index also. So if you want to do any filter operation, we don't need to go to the row and read the complete row to identify whether Justin Bieber is there in this particular segment or not, because it is there in the dictionary, and this dictionary also tells that, I mean, the secondary index tells you that where exactly the Justin Bieber record is present. So which means you don't need to read the complete segment or complete set of data to filter on some particular dimension. Now, on top of that, if you look at that, analytical queries are more in aggregation in nature. Aggregation in the sense, only few columns will be, functions will be applied, or the aggregation query functions will be applied only on few columns. So in this case, so if you are querying only one column, and if the data is organized in a columnar fashion, only one column need to be read directly from the disk. So which means that the data scanning requirement for bringing the data into memory is very minimal. Okay, so that is the key reason. These are the 4 key reasons why Druid is fast from the storage perspective, storage and computation perspective. There is one more point. Okay, so just going before that. Okay, so I will see how the data is organized. So if you look at this, this is a view of how data is organized in a segment. We have time. Time is recorded, and all the data are stored in a dictionary encoded way. So we assume we have 10 columns. Then 10 columns will be stored, which has the encoded values in it. And we will have a dictionary as a part of segment itself. And dictionary, we will have each column holds one dictionary. Okay. So this is one dictionary. This is another dictionary. So state is one dictionary. The page is one dictionary. And mostly what happens is the data will be repeated in a page. For example, there are limited number of cardinality for each data to happen, to land into it or in any database in case of analytical use cases. So in that case, the dictionary will be of a limited size. So dictionary encoding will save a lot of space, as well as it improve the accuracy. I mean, improve the performance. On top of that, we store the reverse index also as a part of Druid segment. Okay. Now, another reason for Druid to perform fast is basically because the rollup. We call this a rollup, but in reality, what it means is during ingestion itself, the aggregation can happen. So, for example, in this case, these are the raw data which is ingested into the Druid. So, if you look at this, Justin Bieber, SF, and there are column added, column deleted, right? So ultimately what happens is if we aggregate this value at the time of ingestion, these 3 rows becomes 1 row. Okay, so this becomes Justin Bieber in 1 row, and SF is SF, and added will be like, it's a sum of values, right? We need what are the sum of addition happens into this particular pages. So that will be added here. So 10, 25, 50. So total it becomes 50. So only the aggregated value can be stored here. So that will reduce the amount of data which is stored in a segment. So in this case, this will drastically reduce the storage requirement as well as computation requirement at the time of query. So this really improved the performance. Okay. Yeah. So yeah. Okay. Now coming to the cost efficiency side. Now just imagine this. I want to retain, say, 1 year of data, but if you look at it, very infrequently, my customer query last any data above last 6 months of data. So what I mean to say is most of the queries happens in the near real time or near recent data basically. So how do I arrange this? So in case if I want to arrange this in a tiering fashion, for example, I will give a set of hardware for storing recent data, and that too is more powerful hardware. In that case, I can store all hot data in the powerful hardware and warm data in lesser powerful nodes, and cold data. Cold data means we will have less CPU and memory, and that can hold more data because it's going in the cold tier. My queries are going to hit the cold tier very less frequently, and that means I can control my cost based on the tiering. So this is one another advantage of controlling the cost using tiering. Now, as you think about it, so most of the time what happens is you may have to keep the data for some period of time. For example, I can keep the data for say 1 hour of I'm sorry. For example, if I'm doing a real-time ingestion or a real-time analysis on a particular use case, in that case, my most recent data will be heavily queried. Like so, for example, in this case, I can keep 1 hour of data in more powerful hardware, and after that, the data can move from 1 hour onwards to a second tier which holds the data for 6 months of time. And after that, the data can move from one tier to cold tier, which holds 6 months to one year of data. So this movement will be automatically handled. And after that, what happens? Now, after that, if I'm not interested in keeping the data any longer, I can define the retention and the data will be removed automatically after that. So that data retention is another key feature which Druid provides. In some cases, I can also specify, I can do a re-ingestion of my old data, and the data can be rolled up with a higher granularity. For example, when I move my data from, when my data is maybe 6 months old, maybe I'm not that much interested in keeping every days of data as is, but I can roll up the data at day level or at the month level. So that the data roll-up will happen. At the same time, the number of records will get reduced drastically here. Okay. So rolling up is another key feature which can control efficiency. I mean, which can control the cost of my Druid cluster. Okay. So this is by natively supported tiering, and data retention is natively supported by Druid. You don't need to write a special code for doing that. Okay. Now, it's a general small comparison why Druid performs better when compared to other open source components. So this is a blog post which is published in Imply blog post. So here is a brief comparison of how Presto and Druid performs. So if you look at it, it's almost in a 30 GB of data. It's Druid performs relatively 24x faster, right? Yeah, so this is a benchmark. Then this is another benchmark on the how it performs against BigQuery. So as the number of concurrency increases, Druid performs really well. If you look at here, the cost for executing a query when the concurrency increases is increasing very nominally, whereas the BigQuery is the cost is shooting up. Okay. Yeah, we will cover some of the use cases which industry is using. Some of the common use cases are clickstream or user behavior analysis and application monitoring, which Ankit will be covering more in detail. Is a good fit for Druid. And some of the other use cases are digital marketing, where the data, the huge data is coming into the data store. So this relatively digital marketing and as well as IoT use cases covers really well in case of Druid. This is some of the strange or heavy use case. I just want to showcase that. Here's how Netflix uses Druid in real time, and Mopup, basically Twitter, is using Druid in real time. Yeah, so they ingest almost 100+ billion records per day. It's almost 1 trillion rows per year. and they having a hundreds of servers, but they will get a sub-second level of latency. So this is a good candidate. Druid is a good candidate to operate in this game. So this is one use case which I picked basically to identify various use cases. This is not limited to anything of which is mentioned as a randomly picked couple of use cases which are in an entirely different angle. Yeah, so this is one use case from Reddit. Basically, they select that events come into Kafka, and from Kafka, the data is pushed into S3. And from S3, some Spark job will run on an hourly basis, and that will push the data into Druid. And previous to this, the data was served by the Spark directly, and it was taking time. Once they move that into Druid, then the reporting APIs respond within a sub-second level of latency. So this is a great experience when compared to the previous implementation. This is one another use case. Druid is being used in AI, basically at the DBS. So I've given the link here. So this talk is more about how Druid being used in the DBS bank. And this use case is basically to train a ML model. And this model is basically more aggregate in nature. So what happens is, earlier they were using Spark for doing this. So what happens is aggregation is, when compared to Druid, it's relatively slow in Druid, slow in Spark. So once they move this use case into Druid, it drastically improves the performance of the training phase. And this is being used in their AML scenario, AML use case. Okay, so what I mean to say, there are use cases, there are usage you can use Druid to feed the ML model with the aggregated results. In this case, so this is a typical case of a BI use case. The screenshot which I have selected is from Pivot itself. Pivot is another product from Imply. So the reason for this is for any BI use case is Druid is really fast in doing the slice and dice kind of performance. The reason being that index is by default created for all dimension. That means you can drag and drop any of the index from here to here, filter, group by, and all those things will perform relatively much faster in a sub-second level latency. So this is a good use case for any BI use case. You can do slice and dice, and Druid performs really okay. Yeah, in Target, if you see, the one analytical engine itself is created using Druid. So if you look at that, so they have created a React UI where user can interact with a React UI. And there is an API REST layer which will control the access control, as well as this create the complex expressions like SQL commands, SQL queries, and that will be fed to, fired to the Druid. The data loading happened from Hadoop and Hive, and the REST APIs, basically the aggregate results are used in mobile application and external application, even in the backend application for dice and slice and dice of their data. So this is a great use case. The entire enterprise analytical platform is created around Druid. Yeah, so this is due to the limitation of time. I'm very happy to discuss more about more use cases, but there is a Druid powered by page where you can see more use cases, how Druid being used in across the industry. Yeah, just want to introduce about a couple of them. Okay. Just want to give a small intro about the community. So we have a Druid forum, druidforum.org, very active community. So if you have any questions, you have anything to share, you can just connect with this druidforum.org. you can stay connected with Twitter, Imply, Imply data, or even Druid.io. I mean Druid.io. You can also connect directly with me. I'm happy to help you in case if you have any questions around Druid. Keep in touch. Okay, so the key takeaway for the today's session is basically we talked about how Druid respond really fast and why Druid is performing really fast. It's mainly because of the way the data is organized in the Druid. And from the cost efficiency perspective, when compared to high Presto, Druid cost is pretty low. Compared to BigQuery, Druid is very, very cost efficient, and a variety of use cases, not just limited to this, what is being showcased. Yeah, time for question. Yeah, okay, so one question is about, yeah, Dharam mentioned that, yeah, so there is a question about Raja Nagendra Kumar. How about influx? So we have a comparison about influx in I think Imply blog. So just do a comparison. I don't remember exactly the URL and all. So there is a Imply influx DB versus Druid. So there is a blog about this. Yeah, exactly this one. So influx DB comparison to it performs really well when compared to that. Dharam talks about ClickHouse comes very close to Druid. Yeah, ClickHouse we have seen is very close to Druid, but there are some challenges across the scalability side. That's it. And Access JDBC driver connect to Montreal OLAP to Druid. I'm not sure about that. I don't know. I need to check that. Okay, so I will get back to you on that part. Any questions? I don't see any questions in the audience tool. Yeah, so there is somebody did a test. Yeah, yeah, your test is accepted. Yeah, that's it. Any more questions? Please feel free to post it. Any slides if you want to cover it once again. Feel free to mention that in the chat or even in the slide. Oh, okay. So does it support join like SQL? It supports, but there are limitations for Druid to support joins. Yeah. So just explore it. Let me know if you need any help in that. By default, it supports, but there are some limitations. We'll talk about this more in detail. So because that is itself is a bigger topic. What is the relationship? What is Imply relationship with the Druid? Okay, so Imply is a promoter of Druid. Almost around 80–90% of commit happens from Imply itself. Imply offer managed service for in AWS. So you can spin up a Druid cluster where the control plane, basically the deployment will be taken care by the Imply, and you can what do you call, spin up a cluster in a matter of couple of clicks. Okay. So that's one offering. Another offering is Imply Clarity. So for monitoring the Imply cluster, we have a product called Clarity. So that helps customers to monitor their Imply cluster, especially when around the performance and stuff like that. That is really beneficial. Yeah, okay. So then I'm talking about Raja, about check out the influx DB, about time scale DB. Um, yeah, another question is how does Druid enhance with Snowflake analytics? I'm not quite sure. Anyone in the audience, if you would like to share, please raise your hand. You can share your thoughts.
I mean, this is Itai, by the way. I'm Tijo's colleague. One option I can think of is, I mean, you'd want to store, maybe an aggregation of your data in order to do very fast analytics. So then you'd use Druid. And other times in the same technology stack, you'd have Snowflake for example, keeping all the entire raw data and stuff like that. So this is what I've seen from some use cases. So they can live side by side in some organizations. Hope that answered the questions.
Okay, thank you. We just crossed 2 minutes. Sorry about that. Okay.
Thank you so much, Tijo. I hope everyone found that super useful. We will be sharing slides and the recording footage probably later today or tomorrow. So thanks again, Tijo, and thanks, Itai, for also helping answer questions. Next up, we have Ankit Nayan. He is the co-founder of Signos.io, and he is going to be discussing their observability use case today. I will hand the reins over to you, Ankit. And you are still on mute, by the way.
Am I good now?
Yes, we can hear you. Thank you.
Cool. So, hey folks, thank you for taking your time out to hear from us. So I am a co-founder at Signos. We are building an open source observability solution. We are using Druid as a real-time analytical data store for observability data. So we'll discuss further into different aspects of what observability is and the different aspects of what data store was needed and why we chose Druid, along with a demo of Signos and how things are working out right now. So first of all, we start with the 3 pillars of observability. Observability is by definition, we try to understand what states of the system are there when we look from outside and given a state that the system is into, right? We try to infer how does the system look like. So today we talk about 3 different components that constitute observability. One is metrics, another is tracing, and third one is logs. Logs we have been very much familiar with more than a decade of free storing of logs into console and elastic search engines and all. Right? Metrics is basically an aggregate of data that you want to listen to. Let's say if you want, how many step counts did you take today is kind of a metric. Prometheus is a tool that is very good in storing metrics, and it gives you different capabilities to query those such kind of metrics. Prometheus is a pool-based system which goes to different targets and scrape the metrics and gives you the power to query them over, right? And tracing is a new third pillar of the category where when a request starts from the load balancer and goes to different applications to the database, a request is being traced down each and every step, and you get to know what events were thrown or started up during those individual steps. So that is tracing. We track down the entire request. So Jaeger is the latest tool that is open sourced by Uber that ingests huge amount of spans or events, and you can go and see an individual trace or the request and see which events were there, right? And similarly in log, we have been using Elastic for a long time, and we tried to visualize kind of have some aggregates that we try to run over the free text of logs, right? Now a new category or a new player is coming up in logs, that is Loki by Grafana Labs, that works towards more on structured logs. By structured logs, we mean is we define a log or by an event or by a structured key value pair of data, right? Like status code is equal to XYZ, time taken is equal to XYZ, and application is equal to P, gateway is equal to that. So these kind of structure, when you construct logs into structure, it becomes very cheap when it comes to storage, because we now don't need to index everything, and it becomes very much easy to query them also. So below are the logos of these individual tools that we use today to get different aspects of observability. The first one, this one is Prometheus, this is Jaeger, this is Elastic, this is Loki. Okay. Now, when you get started with Prometheus, Prometheus is very simple to get started with, right? So you just need to install using Helm install or operator. You get started with small teams. There are various exporters that expose metrics into some formats. You get to know about all that. You can get CPU usage, memory usage, storage usage, network, and if you're using Kubernetes, then kube state metrics also. It has powerful alerts. You can write alert as codes, right? You can version the alerts and you can verify them later in the Git. We have, it's a very advantageous to store your own sort of custom metrics into Prometheus. They are very cheap, and Prometheus is good at storage of data. These are the things that can get very easy to get started with Prometheus. Now, there are a few hard things about Prometheus, like getting application metrics. The standard set of metrics that can be exported in Prometheus is easy, right? But when it goes deeper into applications, what events were emitted, like this is the graph that I'm showing off, like an application is doing a number of external calls, like external calls to cart service, PayPal service, user service, and what is the status code you're receiving? What is the overall duration that external services are taking? What is the duration by different services that you're talking to? So these things become important to boil down the reason why your application is slow. And these things are not by default provided in Prometheus. And Prometheus is not by default horizontally scalable. It's vertically scalable. You need to add more disk and more CPU and memory to make a Prometheus server work. You have to federate Prometheus, or you have to use some tools like Cortex or Thanos to store data for the long term and make them deduplicate the data. Okay. So as for a standard team, it takes roughly 1.5 months to get started with Prometheus. You have to maintain sidecars, or you have to run a lot of exporters to get the data in. You have to do all the sort of long-term storage and application metrics and do these set of kind of things to get it up and running. Apart from that, this is the first aspect that you should be monitoring. When Prometheus metrics go haywire, now you know that there are 10% errors in your application. What do you do next? It does not solve for the next level of questions that come into your mind about how to figure those root causes. Right? So root cause is missing, analysis is missing Prometheus. Right? Now comes the era of distributed tracing. I'm sorry. No issues. Now comes the era of a distributed tracing, where we track each and every individual request down the different services and see how are they performing, right? So you want to know which instance actually broke out, which the deployment version broke out. Is it the upstream or downstream service that is not working correctly? You want to know about those things, right? This is a typical diagram of an Uber's architecture, and you can see how complex it can get when it comes to scale. So Uber gave an overview of an distributed tracing paradigm with some sample application, what we called hot rod, that is ride on demand application. And this is the UI that you see. You can click on these buttons and the driver will be assigned to you. That will be coming shortly. Yeah, this is an example that Uber has shown. This is the Jaeger UI. You can see different services that the request went through, right? And there are a few filters like minimum duration of the events that you that they can filter by and see what went wrong there. So basically tracing a request when it entered your control boundary to the time it hit the databases and gave the response back. You want to know everything. Right? So this is the part where it comes in. So this endpoint is basically /dispatch endpoint from front end emitted 51 spans or events, right? And it had 3 errors. It went through multiple services like customer service, driver service, front-end service, MySQL service, Redis service, route service before emitting the result back. Right? So these are the different services it went through. Now the total time taken by that request was also there. So you need to know a lot more details about these applications. So this is a typical trace diagram that is visible to you when you see Jaeger UI, right? So the list of all the 50 events that were emitted during this request is here. This is the name of the service, the first part. The second part is the name of the event or the name of the span, as we called it. So span is equivalent to an event that is the minimal unit of a trace. A trace is a complete request. Got it? So front-end service calls customer service / customer endpoint. Then it calls the customer service calls MySQL SQL query. On a parallel, front-end service calls the find the nearest gRPC endpoint. The driver service calls the Redis endpoint, and multiple Redis calls are being made. Okay. And apart from that, the front-end service calls another route service. The route service calls /route, and it works henceforth. So in the diagram, you can see the distribution of how the things are going over a period of time. Right? So this request took around 500 milliseconds, and this MySQL query took till 250 seconds. Now from 250 milliseconds to the further down the time, like 430 milliseconds, a lot of sequential Redis calls are being made, right? Because this request ended and the next started. This ended, the next started. So each request is starting after the earlier one has ended. So this means it is a sequential call. Right? So you need to understand the architecture of your application to figure out, right, that does this trace request make sense for you or not, or you may have to improve it. Now, when you click on an individual event here, you will see some information like this. Like when you click the MySQL query, you should be able to see what exactly is the MySQL query. There can be some logs and what kind of, so you can attribute many key value pairs that you can choose to understand your event better later. So these are the common patterns that you need to look out into your distributed tracing data to understand whether they are working correctly or not. Just give me a second. Cool. So in this one, you can see the Redis is throwing some sort of errors, right? So it will be pointed out as red, and you can see error is equal to true flag in your data, right? Now you can see if your distributed tracing diagram looks like this, then you need to figure out what is the longest event that took most of your time, and you would like to optimize on that, right? And when you see a staircase pattern, like I showed you earlier on with Redis, like this Redis, you would like to know why things are going up sequentially, right? Would you like them to do parallelly, or is there some flaw from the deployment angle? Or if we are using an ORM, then ORM may be making some sequential calls to make it work. And also be wary when all the events end at a particular same time. So this might mean that some things are timing out, right? So you have to take care of a few things when you see a list of patterns for your events in your request, right? So these will give you very much detailed insights about how is your request performing when it hits your application. And this is the rough architecture of Jaeger, how it works. Like we have an application that is hosted somewhere. We put up some library or Jaeger client library in the application. It starts sending data to an agent that runs in your machine or VM, which pushes data to a collector. We can do some sort of sampling to see which data is relevant to be retained or processed further. It stores to database, and you have a query layer that that queries your database and shows it to the UI. Right? And you can run some Spark jobs to get some aggregate data. Now, people have been mostly using as Elasticsearch and Cassandra to store these in databases. Right? Now, when you want to use both metrics and traces in your system, these individual pipelines or data pipelines were independent till now. You'd like to have a uniformity in your data pipelines and not 2 or 3 separate pipelines for metric, traces, and logs. Right? So when I tried to run Prometheus with Cortex and Jaeger for distributed tracing, so this is the architecture diagram that I came up with. So this is one of the individual hosts. There are multiple hosts which have many applications running in. There are client libraries in each application that start sending data to OTel collector. And basically this is Open Telemetry collector. Open Telemetry is a vendor neutral or vendor agnostic instrumentation framework that gives you the ability to write code in your own application about telemetry data, and you can export them to different vendors. So these Open Telemetry collectors send data to some proxy. So we need to authenticate via that proxy before sending it to different systems. Now that data is sent to Jaeger collector and Prometheus server both independently, because Jaeger handles the tracing data, Prometheus handles the metrics data. Now it is ingested into Kafka, where Jaeger ingestors processes that data to feed to Cassandra. And Prometheus server has a remote endpoint configuration which sends data to Cortex. Cortex has different components running like distributor, ingester, and many other different components like memcache or something else. And it also writes to Cassandra. So this is the metrics pipeline and this is the tracing pipeline. Both are independent. Even the queries are independent. We have a Jaeger querier that queries about the trace data and a Cortex querier that queries the metrics data. Now you can build your own in-house single UI, or you can use Grafana UI to visualize those data. But a lot of things are lacking here. We should not have idea to separate independent pipelines to get these kind of data, right? So we started looking for other alternatives. Like we need to have a Jaeger++. Jaeger currently lacked a lot of potentials. We cannot harness the open telemetry or the distributed tracing data much today. There can be various different types of slicing and dicing of data. We should be able to run aggregates on them. Like you have an annotation of data like your customer type is equal to gold or your payment channel is equal to PayPal. So these are the common annotations that can be manually added by your application developer. And you'd like to know what is the error rate specific to that customer type. Like you'd like to have different SLOs and SLIs for different customer types. So you should be alerted on them. Right? Moreover, this capability is not there in Jaeger, and you cannot set alerts on Jaeger, right? So these are the lackings that we saw in Jaeger, so that we are not able to fully harness the distributed tracing data. So we decided to build Signos. What we're building in Signos is basically a single pane for both metrics and traces right now. We'll be including logging soon. We should be having powerful trace filtering and aggregation capabilities that is powered by Druid. So we chose Druid to give us an aggregation capabilities over traces, right? So it's a analytical database. So we should be run some analytical queries into it, right? I'll show you a demo where you can see the power of that Druid can that gives to Signos, right? We also set retention rule very easily from the dashboard using Druid. We try to keep it things out of box like that. Like you just get started within a few minutes or an hour, rather than taking 1.5 months to set long-term storage, short-term storage, and different exporters. It takes a lot of time to set those things up. And we also did a cost comparison as compared to Datadog. We were 10x cheaper. So we have written a blog on that also. Now, since things are open source, you will be fully able to control the data and not caught into any such of compliance or regulatory boundaries. Right? You can keep the data in-house. You have better data governance. We have a stream processing architecture that is powered by Kafka and Druid. Right? So now I'll discuss the architecture of signals, how it looks like. So this is the diagram of the architecture of signals. We have different applications as sending data via OpenTelemetry collector route. And that OpenTelemetry collector writes to Kafka topics. Like we have a topic called OTLP span where the data is written to. We have some stream processing going on in Go where we try to flatten the data to be ingested before sending to Druid, because Druid cannot work in nested data. So we try to flatten the data, right? So we write it to another topic called flattened spans, and Druid ingests the data from flattened topics directly and stores into S3. We run a query service that translates your queries into Druid SQL queries and gets the data to front end. Right? So the different components that we work with is OpenTelemetry collector, Kafka, stream processors, Apache Druid, query service, and the front end. Now, why we chose Apache Druid, right? As I discussed before, we need to run some sort of analytical queries on distributed tracing data. We need to slice and dice a lot and run some aggregates. Like if you have a customer type gold, you should be able to run some aggregates based on that or key value pair, right? And we can ingest data real time from Kafka to Druid. That was one of the very positive aspects of that. Now, I also did not want to run 3 different observability data pipelines of metrics, traces, and logs into different ways of storage, different ways of aggregation and storage into Cassandra and different queries to different UIs. Rather, we wanted single data store that can handle all those kind of queries, right? So we found the structured data can be handled very well by Druid, right? So you assign the dimensions, you assign the values, and Druid takes care of it. Moreover, the different components of Druid, like historical parts, the brokers, the coordinators, all are very differently individually scalable. And when we knew that we can write it to S3 for a deep storage, so we were happy, right? So it's the object storage that everyone is happy. It's cheap, right? And Druid is known to handle huge amount of scale. It has been proven at Airbnb, Lyft, Netflix, and Pinterest. So you can go to the Druid's powered by page, and you can see the list of companies using Druid today. I reached out to Druid community to discuss a few things and got good response. So you can reach out to the Google group, the Slack channel in ASF workspace. You can raise GitHub issues. I actually reached out to many different folks who worked in Imply, and they replied also, right? So the community is growing and is responsive. So you like to work in such communities. So this is how the UI of Druid looks like when we are using its signals, right? So we have an ingestion supervisor that creates a data source flattened spans, and it's running, and we store all the past ingesters or tasks into S3. So all those are success, and now it's working perfectly. You can write SQL queries in the query tab and get some data accordingly, right? So eventually all the queries that we write as signals is converted into native Druid queries, and we can query our own data source. So flattened spans is our data store, and these are the different dimensions that we have the data about distributed tracing data, and we query such data. We have service name, span ID, we have tags. So tags is something that is nested, and we have flattened the tags to be queried in Druid. So we use as multi-dimension array in Druid, and we use that functionality. So I'm happy to show you a demo of signals and how things are working. Right. So this is the basic dashboard of signals. So all of this is powered by running analytical queries over the distributed tracing data. So the distributed tracing data alone is not sufficient. You should be able to run aggregates. That is powered by Druid. So this is a front-end application. We can see the P99 latencies, the error rates, the request per second that are coming with each and every service. This is the same service that we see in that we saw in Uber application, that hot ride hailing service that we click a button and the cab comes. Right? When you want to drill down into any of those individual services, you see such sort of graphs. This is a P50, P90, and 99 latency profiles, the RPS, the request per second your application is receiving. What are the top endpoints? Like this is how the different endpoints are performing here. What is the P50, 90, 99 latencies? What are the errors per second? So these kind of aggregates we should be able to run. Now we are building external calls. Like if an application is making external calls, like to different services downstream or to external services like PayPal, you should be able to figure out which part of your application is slow, whether due to external services or not. Right? Now we want to choose a different time frame of data, let's say 1 hour, and we see the graph. Let's see, you see there's some spike here. You want to see the data that is available there. And this is the distributed tracing data that we query from Druid. Right? So we have the front-end service selected. You can add your own keys like tags, keys, and values to filter out the different queries. So these are the individual events that you get of this service, right? So if an application is handling thousands of requests per second, you should be able to get thousands of requests, thousands or tens of thousands of events per second here, right? So, and you can drill down into individual requests. Like this is an individual event when you want to click on it. The trace ID, this is the complete individual trace that consists of 51 individual events, right? So this is again the front-end service, the /dispatch endpoint. It calls the customer service calls the customer /customer endpoint, which calls the MySQL service and the MySQL query. So how much time does this take is 1.48 seconds, and the total time taken was 1.8 seconds. So you should be able to figure out how things are going in a request. Now again, the driver service was called here, like, right? So the front-end service calls the driver service in parallel. The driver service calls multiple downstream Redis service to get the details about the driver ID. So these kind of queries you should be able to figure out will help you debug a lot about your application, right? Next, we go back to our application to see distributed traces, right? So this is all the distributed tracing data that we have, and there can be tens of thousands of those applications. Now, like an example, I said, like we would like to run aggregates on distributed tracing data, which is not possible in any other tool today. And this is also powered by Druid. So like a key value pair of customer type is equal to gold, we have something called http.url, which is the external endpoint is being called, right? So there's a service running at 8081 port, and we want to see how things are performing there, right? We filtered using those two tags, the service name and that key value pair. We are saying what is the duration of the different events here, but we now want to see what is the overall aggregate of this one, right? So we want to see what is the overall duration, P99 duration of all the events that are filtered by these filters, right? So this is the 99th percentile duration of this, right? So if you had something like customer type equal to gold, you should be able to see the 99th percentile profile of that key value pair, right? So this is something specific to us. We are also building service maps that is coming. You should see a list of all the services that your 1 service, 2 service, 3 service, 4 service that your application is interacting with, and how is the health of those services. How is the usage usage of your application, like how many events data are you sending every day, and over a week, how is it looking? So you should be able to do some sort of capacity planning according to that, right? So this is what we are building at Signovs. Like coming back to slides. So now you have an idea of what we're building at Signovs. Like, so what are the steps needed to get to that dashboard, right? You just need to install signals, right? So go to GitHub profile, git clone the GitHub, go to deployment folder and run a script .install.sh. This shall install signals, which is the backend for the OpenTelemetry data, right? So you shall install the hotel collector, the Apache Druid, Kafka, UI, everything. Now you need to put something in your application that will be sending the data out, and that will be using the OpenTelemetry client library, right? So here I have given an example of using the Java jar file that is there by OpenTelemetry. You need to just set the OTLP endpoint, right? Like the endpoint where signals is hosted. You should be able to give that endpoint, and you need to give the name of the service that you want to monitor, and just run it as usual using the ---- Java agent command. So it will start sending the data. It actually works in minutes, right? So what are the upcoming features in Signals? Like we are trying to build an external API monitoring, like I said, that will give you an example, like whether your application is slow or your downstream services are slow. And we are also building service map. Sorry. So we have an open source alert manager, Jelena. Is that Jelena? Yeah, I think we're sorted now. Yeah, cool. So we have service map coming. We have open source alert manager that will be coming. That is inspired from Prometheus. That will give you the ability to have different silencing and grouping of alerts, and alert as code facility will be there. That's so that you can version control the alerts, and you can send custom metrics to Druid also. For huge scale where we have millions of events coming per second, you should have some sort of sampling to restrict the amount of data that comes, right? So you need to set properly set retention of data. So you need to have some sort of control on the events coming per second. So that can be done using sampling. We will be building an open source anomaly detection framework. So that will be pluggable with Signals and is missing today in the open source world. Like you have Prometheus metrics, you should be able to plug some open source tool to do anomaly detection in your metrics and be notified via some alerts, right? So thank you being a wonderful virtual audience. I think I hope it's difficult today to do virtual meetups, but we are happy to help you out any ways, and looking forward to meet you in person sometime soon. So you can reach out to me on Twitter, LinkedIn, or Ankit at signals.io.